All right, welcome back to the Woodshed, I like to call it, which is my studio here, Hanson Studios. So welcome back to the next episode, the next lesson. Today we're going to be doing 8.5, or just this video. You guys are watching these hopefully at your own pace, that is comfortable for you. I'll get them out as quick as possible. I had to do some troubleshooting with technology here, but I want these to be efficient and easy for me to do and for you to watch and upload and download, and well, hopefully you don't have to do any of that because now you can just click on YouTube videos. But it took me a while to get this set up, so here we go. We're doing 8.5 is the section in your book if you want to follow along. Our objective is what we're going to learn is going to be how to calculate the following things, which are going to be the theoretical yield, the actual yield, and percent yield. I put limiting reactant in the bullet point, but that's not actually something we're calculating. The limiting reactant is really the main focus of this lesson, and actually is what all this kind of centers around. So we'll do a lot of talk about the limiting reactant, and we'll talk about like how to identify it. If you were to pick a verb, that would be the verb, identify the limiting reactant. But our learning objective is not just to identify the limiting reactant, but once we do that, to then calculate the following: the theoretical yield, the actual yield, and the percent yield. So I've got it so that you can follow along with me in the keynote presentation. I actually even uploaded this to Google Classroom weeks ago, so if you want to look at that, you can just look in your textbook. It's basically just what's in your textbook. So without further ado, you know what, actually I wanted to have a worship thought, kind of keep in consistency with how we normally operate class. And I did have a thought on this that's pretty relevant to limiting reactant. So in the Bible, a lot of the stories that happen, and even in our own personal lives, speaking of my own, I noticed that one of the limiting reactants or limiting factors in my life with my relationship with God and the events that happen is my faith. And you see that, like, again, all throughout the Bible, that people's faith will often hinder what God does. Not what he can do, but what he does. And I think it's interesting how almost like a lot of the parables, whether it be rubbing mud in your eye or washing in a river 7 times, or, small acts of faith were required for God, or it just seemed like they were part of the equation. I'm not going to say required. Like, I don't know if God sits back and is like, if you don't do it, I'm not doing it. There are times when he acts without us acting first, but oftentimes we're part of the equation, which I think is really cool, but we're a small part of the equation. But it's like, if we don't do our part sometimes, then God won't do his part, which is way bigger. And so there's a pretty neat equation out there I found online that says, it's a math equation. So it says small faith plus big God equals huge results. So obviously most of the huge results are coming from the big God, right? But the small faith is part of the equation. So I think it's a privilege that we get to take part in that. And that's more honestly what I think is the reason that faith is part of the equation, is so that we're part of it. We're included in it all. And so it's a relationship thing. It's not just that God needs our faith, or that he's demanding it for us to ask him first or whatever, or give first. But oftentimes he just wants to include us as part of the equation so that we feel part of it. And so anyways, but again, that can oftentimes be a limiting factor. When just a little bit of faith is required, but it's not there, nothing gets produced, when a ton of stuff could have got produced. But anyways, so you'll see with chemistry, there's such a thing as this concept of limiting reactant that prevents the productivity of a chemical equation. And so let's just jump right in here. I'm going to use my iPad here. And we're going to start actually by looking at this analogy that we first looked at, dealing with the pancake recipe. So hopefully you guys aren't sick of this pancake analogy. It's so perfect for describing what this chapter is about, and making it so that it's kind of more easy to understand. So all chemical equations, remember, are like recipes. If we were to look at this real recipe, we simply have 1 cup of flour plus 2 eggs plus 1/2 a teaspoon of baking powder will produce 5 pancakes, right? We looked at that last time, and we saw that we can use this chemical equation as a conversion to make conversion factors, as a way to make conversion factors, because these are simply relationships that are always going to exist. Now, could you make 5 pancakes with only 1 egg and but still having 1 cup of flour and half a teaspoon of baking powder? Probably, but it's going to be kind of a loose pancake because the eggs kind of hold things together with texture. Now, could you make it without the baking powder? Yeah, probably, but you wouldn't have, the carbon dioxide production, so you wouldn't get the fluffiness of the pancakes, because that's where the air bubbles come from, is the CO2 produced by the decomposition of bicarbonate there upon thermal energy being applied. So when you heat it up, the baking powder releases carbon dioxide. Could you make it without the flour? Probably not. Like, you got to have that. But the point is, even though we could maybe step outside the lines here, we're going to pretend that you can't. You cannot step outside this recipe. Like, these are the ratios that these ingredients always come together if you want 5 pancakes. Because in chemistry, that is how it works. So we have to stick to the recipe. Okay, let's go now to this page here. Excuse me, here we are. 8.5, more pancakes. All right, we're going to return to the pancake analogy, it says. And they've written the recipe again there for you so you can see it. And let's suppose, though, that let's say we went into the kitchen and we wanted to make a bunch of pancakes for a family, because we had a whole bunch of family in town. And we looked in our cupboards and we pulled out the ingredients, and we were going to follow the recipe, yes, but we are simply just going to start using our ingredients and make as many as we can. And so what we notice is that we have on the counter 3 cups of flour, we have 10 eggs, and we have 4 teaspoons of baking powder. Which one of those ingredients do you think, let's take that out of the picture for a second. Which one of those ingredients do you think, how about this? Which one of those ingredients, again, you have 3 cups of flour. So 1, 2, 3 cups of flour. You have 10 eggs, so about a dozen, but you used 2 the other day or something, I don't know. But you got 10 eggs, and you got 4 teaspoons of baking powder. Not very much, but got 4 teaspoons. Which one of those do you think is going to prevent you from continuing to make pancakes, assuming you stick to that recipe? It's kind of hard to say, right? You don't really know, because you got to kind of look at the ratios and the relationships between the way those ingredients come together. Now, someone who first comes in the kitchen might go, "Man, you hardly have any baking powder, so it's probably going to be the baking powder. It's going to run out," right? But you don't use very much per pancake, do you? Some people might say, well, it's the eggs, because you only got 10 eggs. You're probably going to make what, 10 pancakes? So you got to know the recipe. That's kind of what the point is. It's not really intuitive. So scrolling down here, you can see that if we did what we learned in the last lesson, which is convert the ingredients and convert anything in the recipe to the product using the conversion factors. Remember, that's what we learned last lesson, is how to use the recipe to make conversion factors. We can see that it's actually not going to be the baking powder. In fact, if we were to use up all the baking powder, I'm just going to jump right to the gun here. That the third problem down here, if you look, they've done three problems. If you look at the bottom one there, 4 teaspoons of baking powder converted to pancakes yields 40 pancakes. All right, the 10 eggs yields 25 pancakes, and the 3 cups of flour, which you think you'd have the most of, so it wouldn't run out, it was really only yielding 15 pancakes. So lo and behold, the baking powder, you've got plenty of it. Even though you only had 4 teaspoons of it on the cupboard, you're able to make 40 pancakes with that. But that's only if you have the other ingredients. And so you see what we've done here? What we've done is we've determined how many pancakes each one of the ingredients would allow us to make independently. So we said 3 cups of flour. How many pancakes could we make, assuming we had the other ingredients? Well, we could make 15. We have 10 eggs. How many pancakes could we make there? Again, assuming we have the other ingredients enough, we could make 25 pancakes. And finally, with the baking powder, if we had enough of the other ingredients, again, you always have to say that assumption, then how many pancakes could you make? If you were allowed to use up all the baking powder, it would be 40 pancakes. And so you might be optimistic and thinking positively about making 40 pancakes, but how many are you actually going to be able to make? It's only going to be 15, right? Because that's all the 3 cups of flour will allow you to make. So here we go. We're already getting to this concept of a limiting reactant. It's kind of self-explanatory in the term, limiting reactant. Sometimes it's called limiting reagent. A reagent and a reactant are simply the same thing. But the definition is simply the reactant that makes the least amount of product. Doesn't that make sense? So back to our learning objective, if you want to determine the limiting reactant, you just need to find out which one of your reactants is going to make the least amount of product. And if you have more than one product, just pick one and do an analysis, do the math, and see. Use the same product and do an analysis of all the ingredients. I should say all the reactants. And after you analyze each reactant and its productivity towards the products, whichever one's making the least amount of product, there you go. There you have it. That's the limiting reactant. And then since you had to do a lot of math to do that, to figure out that limiting reactant, then guess what? You're pretty much 90% the way there. All this other stuff here that's below, these yields, these are just simply going to be simple calculations. For example, the first one, theoretical yield, that is literally related to what your limiting reactant is. So whatever your limiting reactant allows you to make for your product, that's your theoretical yield. So let's look at this analogy here. If the 3 cups of flour was our limiting reactant, which in this case all you have to do is just say flour, you don't have to say 3 cups. It's not a calculation. The limiting reactant is just an identification. We just identify the flour as the limiting reactant. And if that limiting reactant only allows us to make 15 pancakes, then that's your theoretical yield, 15 pancakes. Okay? Your theoretical yield is always referring to the product. It's always here's the definition, write this down or highlight it or whatever. The amount of product that can be made in a chemical reaction based on the amount of limiting reactant. So you can see there's a huge relationship between limiting reactant and theoretical yield. If you want to frame a sentence, again, there you have it, and we just read it. The limiting reactant determines what your theoretical yield will be. Your theoretical yield is based on what your limiting reactant is and how much of that limiting reactant you have. All right, so let's look at that pictorially. The book on the next page has a really good image that we can analyze or we can look at. You see the 3 cups of flour there? I know when I first looked at that, I thought those were like pots and pans, but those are just really large scoops of flour. I think they're trying to show you that, hey, you got a lot of flour there. Well, I guess if it's all to scale, then that would be about the size of a measuring cup, because look how big those eggs are. The 3 cups of flour is your limiting reactant, and so that's why the arrow is pointing there. The eggs will make 25 pancakes, and the 4 teaspoons of baking powder will make 40 pancakes. So there's a nice little picture just kind of showing you, hey, each ingredient will make the following amount of product, assuming again that there's plenty enough of the other stuff to go around. And so look all the way over there to the left, the 3 cups of flour, those are the limiting reactant. The flour is the limiting reactant, and the amount of pancakes, the product, is the theoretical yield. Okay, let's carry this analogy just one step further. Okay, let's say you actually go into the kitchen to do that, and you're in a hurry. Maybe Gordon Ramsay comes in and he's telling you got 10 minutes left to make these pancakes. And Gordon Ramsay's yelling at you, and you accidentally burn 3 of them. 1 falls on the floor. And so even though you had enough flour for 15 pancakes, you're really only finished with 11 pancakes. Because again, you dropped 3. And you burned 3, and you dropped 1. And so you really only made 11 pancakes. And so 11 pancakes would be your actual yield. 11 pancakes would be your actual yield. And that's calculated experimentally. You got to do the work, do an experiment, do the cooking, do the whatever, do the mixing, make the chemical reaction occur, and then you got to measure. So this is often done in a lab. The last 2 are very lab focused. You're going to get an actual yield. If you're reading a word problem, they're just going to tell you what you actually got. And then when they tell you that, they're going to want you to determine in a percent. right? Like, how well did you do? Well, in this case here, Gordon Ramsay wouldn't be so happy. He'd say, well, you made 11 pancakes and you were supposed to make 15. That's only 73%. You guys know how to calculate that, right? A percent yield is just simply how well you did over how well you should have did. Or in other words, what did you actually get over what you theoretically should have got? All right? What did you actually get over what you theoretically should have got? So you actually got 11 when you theoretically should have got 15, and so 11 over 15 is essentially 73%. So I know you guys know how to calculate percents. So those last two are simple. They're very experimental based though, and so that's kind of like usually an extension to the problem. You'll be given a word problem that makes you do a lot of calculating, determining the theoretical yield by figuring out what your limiting reactant is. That's kind of most of the work. And then these two are just kind of extensions to the problem, either in lab or just in the word problem, they'll give you some hypothetical scenario and they'll say, well, you actually only did this. And so anyways, oops, I thought I just had never mind. Okay, back to the book here. Limiting reactant. Here's a great summary. I love this. This is something you might want to highlight or circle in your book. To summarize, the limiting reactant, which is what all this is kind of based upon or centered around, or limiting reagent, however you want to say it, is the reactant that is completely consumed in a chemical equation. Ooh, check that out. That's a new definition. So the first definition we said, which probably has the most relevance, is that your limiting reactant is the reactant that is going to make the least amount of product. That's your most probably best definition. But the other definition, which is essentially true, is it's the reactant that's going to get completely used up, and then you're just going to have excess of other stuff, right? So could you have two reactants can be completely used up? Yeah, you kind of could, couldn't you? If you came to the counter with the right amount of ingredients already measured out, because you intentionally did that, then you would. So which one would be your limiting reactant? You'd essentially have two limiting reactants, I guess, and then the rest of the stuff would be excess. If you had it, you could have three limiting reactants technically, but usually you only have one. Usually, because we don't always come to the counter with exactly what we need. We like if I go into my lab, I've got chemicals in stock, to last me for a long time, and then I'm only going to use part of it. Well, sometimes I run low and I say, man, I got tons of vinegar or acetic acid, but I only have a little bit of steel wool. So based on the amount of steel wool I have, I can only do so many experiments, even though I have a ton of vinegar or acetic acid. So let's look at how that would look, sound, and appear with a real chemical reaction. Let's stop talking about pancakes now. The chemical reaction here, if we consider this one, is, and I'm going to read it just like you should a recipe, okay? So that you can kind of hear it in your mind and kind of read it the same way in your mind. 1 mole of titanium coming together with 2 moles of chlorine gas will yield 1 mole of titanium chloride. All right? Why did I not say titanium tetrachloride? Because that's how you name covalent compounds, and this is an ionic compound, right? You have a metal and a non-metal, so you simply say the metal and then the non-metal with "ide" at the end, so titanium chloride. All right, so there's our recipe. Pretty simple recipe. Basically, we got two chlorines coming together with every 1 titanium to make that compound. So if we begin with 1.8 moles of titanium and 3.2 moles of chlorine, what is the limiting reactant? Okay, let's stop here for a second. A lot of students will read these problems and they'll say, well, I have less titanium, so I'm probably going to run out of titanium first. But you have to be careful because the recipe is not always one-to-one for things coming together. Sometimes, like you do in this case, you need 2 chlorines for every 1 titanium. So don't just look at your numbers that are given to you in the problem and start trying to guess or come up with logical, intuitive answers here. you have to do the conversions. You have to take that 1.8 moles of titanium and convert it using a conversion factor to moles of titanium chloride, which is the product. And you have to do the same thing for the chlorine. You have to convert that 3.2 moles of chlorine that you have to moles of titanium chloride or product. And then you compare. And so if you want a solution map, there you go. At the bottom they have the purple squares to the red squares. That's just simply a solution map. And they're saying, hey, to get from the purple square to the red square, you need the following conversion factor just below that arrow. And both those solution maps end in the same result. They end in moles of titanium chloride or product. But one started in moles of titanium, the other started in moles of chlorine. And so they're going to give us different amounts of titanium chloride. And if you just turn the page, you'll see what those are. Okay, and you'll also see the conversion factors they used. Again, you have to be able to look at these recipes or chemical equations and be able to set up a various amount of conversion factors that you would possibly need. Okay, looking at the ratios that the ingredients come together or that they're related to each other. And so in this case, just like I said, the 1.8 is smaller than the 3.2, but that's actually not your limiting reactant. Because you use 2 chlorines for every 1 titanium, the fact that you only had 3.2 moles of chlorine, which is even more than the titanium, is still you're going to be your limiting reactant, because look how much product you get. That's all that matters. How much product are you going to make? And in this case, the chlorine's only going to allow us to make 1.6 moles of titanium chloride, where the amount of titanium would technically allow us to be able to make 1.8 moles of titanium chloride. But which one are you going to make realistically? Only the 1.6, right? Because that's all the moles of chlorine will allow you to make. And so at that point, you've done most of the work, because now you have determined what the limiting reactant is. You just simply say chlorine. You don't have to say 3.2 moles of chlorine. It's not a calculation. It's just an identification. And then you can know what the theoretical yield is. You calculated it there. It's that 1.6 moles of titanium chloride. That's your theoretical yield. Check this out. A lot of students make a common mistake here. They'll see, ooh, the 1.6 moles of titanium chloride is smaller, so their brain will just immediately want to tell them that that's the limiting reactant. But no. That's product. Number one, that's product. That's not even a reactant. And yeah, it's all wrong. Don't make that mistake. Okay, the chlorine is your limiting reactant. It's based on that fact that it's only allowing you to make the 1.6 moles of titanium chloride, which is smaller than the titanium would. And sometimes you can have 3 or 4 different reactants. You don't always just have 2. And in that case, you'd literally have like 3 or 4 different trials you would have to run to see what each reactant individually, just like the pancakes, you had to go from flour to pancakes, eggs to pancakes, baking powder to pancakes, and compare, all 3 of those to each other. Here's another chemical reaction. Let's look at this one together. 2 moles of aluminum come together with 3 moles of chlorine gas to make 2 moles of aluminum chloride. The book loves chlorine gas, don't they, as a reactant? They must have a lot of it and do a lot of reactions with it. That actually is a very common reactant. But if you begin in your lab with 0.552 moles of aluminum and you have 0.887 moles of chlorine, what is the limiting reactant? And the theoretical yield of aluminum chloride in moles. By the way, all this is in moles today for this video. The next video we'll be able to kind of do the same stuff, but yet we'll consider it in grams. So we have, again, those 2 amounts of aluminum and chlorine, and what we got to do is just convert those amounts to the amounts of product that we can make. And so simply converting moles of aluminum to moles of aluminum chloride and comparing that with the amount of aluminum chloride that the moles of chlorine could give us, then we can get an answer. And that's on the next page. And again, you can see the conversion factors they use to do that, right? It's a 2-to-2 relationship between aluminum and chlorine, or aluminum and aluminum chloride. That's the same thing as a 1-to-1. So that's why you literally have the same amount of aluminum chloride as you have aluminum, right? However much aluminum you have, that's exactly how much aluminum chloride you can make. What about the moles of chlorine, though? The moles of chlorine has a 3-to-2 relationship, a 3-to-2 ratio between moles of chlorine to moles of aluminum chloride. So we're using that 3-to-2 ratio as a conversion factor, and we're setting that conversion factor up strategically and intentionally so that we cancel moles of chlorine and that our new unit is moles of aluminum chloride, right? So we're comparing moles of aluminum chloride to moles of aluminum chloride. And which one's smaller? The 0.552, right? So that one's going to win. Now, is that our limiting reactant? No. So that's a mistake that students will make. That is going to be your theoretical yield, but that theoretical yield is based on the aluminum, which is your limiting reactant. Okay, the limiting reactant is going to be what makes the smallest amount of product. Remember that. Okay, so just as an extension here, because it doesn't look like they give you any examples to do this. This is funny. What if we made 0.444 moles of aluminum chloride? Then what would our actual yield be and our percent yield be? Can we calculate that? In other words, well, yeah, I can do it here. I'll just write over or right up top or something. What if we had 0.444 moles of aluminum chloride? Then what would our actual yield be and what would our percent yield be? Sorry, that's a decimal there too. Well, your actual yield is literally that right there. I just told you. You actually got 0.444 moles of aluminum chloride. Now, why would that be? Why would you get less than what you theoretically should get? Well, it's because you're constantly moving and transferring materials, and you either spill it or it gets stuck to the filter paper, or, and as you filter and collect and move and transfer, and you're not always going to recover 100% of what you're trying to get. And so if you only got that much, but you should have got 0.552 because that was your theoretical yield, that's what you theoretically should have got, then you can see how well you did. Just simply do that division problem and you'll have a number that you can multiply by 100 to get a percent. All right, so hopefully that video finds you guys well and can get you right into the next lesson. I'm going to immediately film another video here getting you ready for a lab. There's a really cool simulation on that PHET Colorado website that you can actually manipulate the molecules and add more and add less and really kind of see what's going on pictorially. And so I'll give you instructions for that when I post that assignment on a Google Classroom, and I'll count that for a lab. And then hopefully that'll be directly helpful for you. You could actually probably do that before you even do the homework problems. Speaking of homework problems, you can see that, let me clear that. You can see that the book is telling you at this point you could do these for practice. You could do 43 through 50. Remember, I only gave you a certain amount of problems to do and I omitted some. So if you want to practice some that we just tried, try 43 through 50, but you don't have to do any of the ones I didn't tell you to do. And if you see any that are still under this category at the end of the chapter with limiting reactant and such, but it's in talking about grams, then watch the next video for that, because the next video is going to be talking about how you can do all this same stuff, how you can do all this same type of stuff with theoretical yield, actual yield, and percent yield, and limiting reactant, but yet the problem is going to be giving you grams of substances, and they're going to be wanting answers in grams of substances. So it just requires a couple extra steps, but same concept. So again, hopefully this finds you well, and thanks for watching and all your hard work. Adios.